Okay, everyone, here we are, Chapter 9, Organic Chemistry. That term organic has a lot of different meanings and a lot of different usages, but here in chemistry we'll find it to be the chemistry of carbon, and that's strictly the way we'll be using it for this chapter and for the remainder of the course. Some of the first things we'll do, we'll define the term hydrocarbon, and we'll recognize key structural features and properties of the alkanes, alkenes, and alkynes. We'll also identify hydrocarbon molecules as alkenes, alkanes, or alkynes and name them accordingly. We'll define the term aromatic when we talk about aromatic compounds and recognize the key structural feature that such compounds share. And we'll also name some simple aromatic hydrocarbons. Once we get the hydrocarbons down, we'll also look at how we name a halogenated hydrocarbon given its formula and write the formula for such a compound if you're given its name. So we'll be able to go both ways there. We'll classify an organic compound according to its functional group or functional groups if there's multiple types present. And we'll also explain why the concept of a functional group is useful in the study of organic chemistry, and even more so as we move into biochemistry. We'll recognize and write the formulas of some simple alkyl groups, and then recognize the general structure and properties for an alcohol, a phenol, and an ether. Once we can recognize those types of compounds, we'll also be able to name simple alcohols, phenols, and ethers. We'll name simple aldehydes and ketones and list their important properties, also be able to identify them. We'll name simple carboxylic acids and esters and list their important properties. Then we'll name and write the formulas of some simple amines and amides. And we'll recognize the structure and characteristics of heterocyclic compounds. And finally, lots to do in this chapter, but finally we'll identify some greener, more environmentally friendly solvents. We'll use some renewable resources in organic syntheses and also use energy-efficient sources for chemical reactions. So lots to accomplish. Let's get right down to it. Okay, so organic chemistry, as I glibly said earlier, it's the chemistry of carbon, and technically there are some inorganic forms of carbon like diamond. So to be specific, organic chemistry is defined as the chemistry of hydrocarbons and their derivatives. So of the tens of millions of known chemical compounds, over 95% are compounds of carbon. And why we study organic chemistry at this point in the semester is it's also the key type of chemistry done in the human body and when we move into biochemistry, one of our next topics. So organic chemistry, hugely important. Carbon, a very versatile element. Not to say there's not a lot of other things happening, very interesting things with other elements, but pretty much carbon is king for predictable, understandable chemistry, especially as we think about chemistry of human body and other animals' physiology. Alright, so why all this fuss about carbon? Well, carbon is unique in that carbon atoms can bond to each other to form long chains and rings. That's not the only element that does it, but it really does it nicely, and it does it in a more controllable way than a lot of other elements. Iodine, for instance, can do what's called catenation, this idea of combining with other atoms of its type and forming long chains. Boron can make some interesting clusters and rings, but carbon has just the versatility that no other element has, and for that reason, life on Earth is carbon-based, and being carbon-based, we're obviously quite interested in what carbon can do and the different compounds, the many, many millions upon millions of variations of compounds that carbon can make. Now, we've already gone into a little bit of the uniqueness and versatility of carbon. So the hydrocarbons are the simplest organic compounds, but by no means are they always simple. You can get fairly complicated, not only with the structure, but also with the naming for these hydrocarbons. So they're simple as far as carbon goes, but as we said, carbon doesn't do anything simply. So the hydrocarbons themselves are entirely composed of carbon and hydrogen. And we'll also talk about derivatives of hydrocarbons, and that's where we get some other atoms like oxygen. That will make things a lot more interesting for those of you who are waiting for the biochemistry unit. Okay, so if hydrocarbons are the simplest carbon compounds, alkanes are the simplest hydrocarbons because they contain only single bonds. So since all the carbon-carbon bonds are single bonds, we also will refer to these alkanes as saturated hydrocarbons. Carbon-hydrogen bonds have to be single bonds, but carbon-carbon bonds, as we can see, can have some unsaturations when we talk about alkenes and alkynes, but the alkanes are saturated. There are no multiple bonds between carbon atoms. The simplest hydrocarbon is methane, CH4. This is the primary component of natural gas for anyone who uses natural gas at home for heating or for cooking. It's overwhelmingly methane. There's probably a little ethane in there and maybe some other things, that sulfur-based compound to give it the smell so that we know if there's a natural gas leak. Methane is the simplest, and that's to the left there, CH4, carbon at the center, bonded to 4 hydrogen atoms in the shape of a tetrahedron. And then ethane is just to the right there, and that's again another component of natural gas, much smaller amounts. And so ethane has 2 carbons with a single bond to each other, and each of those carbons has the remainder of its 4 bonds, the 3 remaining bonds as single bonds to hydrogen. That would give ethane a formula of C2H6. Okay, so carbon tends to make 4 bonds. When all those bonds are single bonds, we have alkanes if we're only dealing with carbon and hydrogen. So the general formula for an alkane is C sub n H sub 2n plus 2. And we just saw on the previous slide, here's an even larger image of methane on the left. So CH4, C1, H2 times 1 plus 2, that's where we get the CH4, right? Whenever there's a subscript of 1, we don't show it in the formula and we don't say it, but we learned that way back when, right? If we look at the compound on the right, ethane, now we see we have the 2 carbon atoms, so it's C2, and then we have H2 times 2 plus 2, so we end up with C2H6. We have to be a little careful when we get into the ring structures because the carbon ring will close on itself. We can't use this formula for rings, but for straight chains and branch chains and anything that doesn't have a ring in it, that's truly an alkane. Just carbon and hydrogen, all single bonds. This general formula of Cn H2n plus 2 makes it really easy for you to be able to predict the formula from the name, or to get the name out of the formula once you've reviewed these Greek prefixes we'll talk about. Okay, so on to our Greek. At least eventually we'll get to some Greek. But the names of the alkanes consist of the prefix denoting the number of carbon atoms followed by the suffix -ane. So alkanes should end in -ane. If we look, we've already talked about methane and ethane, which are 2 of the unusual names. Right, they're one carbon atom gets the meth prefix, like methamphetamine has a methyl group on an amphetamine type structure. So meth refers to 1 carbon atom, or 1 atom in a carbon group, is a substituent, a term we'll use soon. And then eth for 2, ethane, or ethyl alcohol, the alcohol we can drink as human beings once we're of age. Prop is our prefix for 3, and bute is our prefix for 4. Then we get into the more regular Greek prefixes, pent for 5, hex for 6, hept for 7, oct for 8, and non for 9. And then, of course, for our purposes, fortunately, we'll end at dec, although we can go up undecane and duodecane for 11 and 12. For our purposes, knowing those first 10 by heart is all you'll need for this course. In the future, you might want to or need to commit more to memory, but for us, we'll memorize those first 10. And those first 4 tend to be a little tricky because they're not the Greek roots for those number of carbon atoms. So mnemonic I learned way back when, as a high school student, believe it or not, was most elephants prefer buttered popcorn. If that helps you to remember the meth, eth, prop, bute part. Pent, once you get there, you should be home free, back to Greeksville, but before that, you might have some trouble with methane, ethane, propane, butane rather, for the hydrocarbons that are alkanes. Okay, so hopefully getting a little more familiar with the naming. Let's also talk about the way we tend to represent these things. Ball and stick models, like you see in A there, the top right, that's generally a comfortable way to build them because you may even have a molecular modeling kit. I didn't require it for the course, although I wondered about it because they are helpful. So hopefully, if you have a little disposable income and you can find a cheap enough kit on eBay or wherever, you might pick one up. But it does help you to get your mind wrapped around these compounds that we'll be making. B, the space filling model, is a little more realistic, right? And they do have some space filling kits out there. They're very expensive, but they do a nice job of showing you what the molecule would actually look like in 3 dimensions. Again, they're all models. None of them are quite perfect, but the space filling model is a lot more realistic than the ball and stick model. The ball and stick models are easy to use, easy to manipulate, relatively cheap, but of course there's no stick between the atoms in 3D space. They're just sort of sharing that outermost electron cloud, and so the space filling models do a much better job of representing that bonding pattern. So sometimes it's convenient to use what's called a condensed structural formula so that you're not drawing in every hydrogen like you might do with a complete structural formula, but you're also giving a good idea of how things are connected. So in the condensed structural formula, those CH bonds, the lines aren't shown because it's just assumed that the C bonds to those H's in single bond fashion. That's all we can do with carbon-hydrogen bonds, right? You can't do multiple bonding with hydrogen. And therefore, we can tell that this propane molecule has a CH3 group, a methyl group on one end, and then a CH2 in the middle, and then a methyl group on the other end. So the carbons are bonded in a single bond fashion to one another, so you have a 3-carbon chain, and then all the rest of the bonds are just hydrogens to terminate. So instead of drawing in all those bonds, we show it as this condensed structural formula, and that tends to be pretty convenient for us, especially as we're getting used to the way that organic compounds are represented. Alright, the straight chain alkanes represent what we call a homologous series. So that just means we differ by the number of spacer CH2 groups that we have. And so any homologous series will vary in a regular, predictable pattern. And if you look at that table 9.2, you can see methane to ethane to propane to butane, all the way down to decane. We've just added another CH2 spacer group in the middle. So that carbon is bonded to the other carbons in the chain. And then above and below you have a hydrogen bond to carbon to hydrogen to complete the 4 bonds that carbon will make. So when we throw in a CH2 group, that carbon has 2 bonds to hydrogen and then makes another bond with each of the neighboring carbons in the middle of the chain. You also see that things get very complicated very quickly. Once we go beyond propane, we can get a lot more isomers, right? Propane, we have to have the carbon atoms bonded 1, 2, 3. But once we get to butane, now we could have a CH3 group coming off the center carbon, which would then be down to a CH group. It gets really complicated. There, we can have 2 isomers. Once we get more and more carbon atoms in our formula, we can have lots and lots of isomers, down to 75 isomers for that C10H22. 75 different ways we can put together an alkane that will have that formula. So obviously organic chemistry is very versatile, and that's why 95% of known compounds are organic compounds, because we can make things very, very different and complicated very quickly once we have that carbon building block. So I threw out the term isomer in that last table. We saw the number of isomers possible, or at least the number of compounds with the same molecular formula but different structural formulas. That's what we mean by isomers, and that feature of carbon in particular, once we get beyond 3-carbon hydrocarbon, we have the ability for what's known as isomerism. We have the formula that can describe multiple structural formulas with one molecular formula. And so you see on the side we have a straight chain butane, And then we have that other variant I talked about where the 3-chain, the propane, is the main chain, and then there's a methyl group off that center carbon, which now has only one other hydrogen. So obviously isomerism, those are the two isomers with the formula C4H10, but once we get to more carbon atoms, we can have many more isomers possible because of how we can connect them. And this is where, if you have a kit or can pick up a kit cheaply, you can build these things and prove it for yourself how versatile carbon is. If we go back to that simple idea of just having a straight chain of hydrocarbons, here we see some of the physical properties, uses, and occurrences of saturated alkanes, starting from 1 and going all the way up to 20, skipping some there as we get in the higher numbers. But what you should notice is the first few are gases, right? Propane's a gas that has a boiling point not too much below the room temperature, so oftentimes you'll see liquefied propane as a heating fuel for homes or for gas grills. So it's easy enough to liquefy because it's not very far from the liquid state. If we just give it a little pressure or cool it down a bit, we can make it liquefy. Butane has a boiling point of roughly 0 Celsius, so butane's even easier, and you'll often see butane lighters. If you look at cigarette lighters or other types of lighters for fireplaces or such things, it's a common lighter fuel because it's so close to being a gas that it's not too hard to liquefy. And then we get into liquids and a lot of gasoline components, right? There's an octane rating on gasoline. You expect that to be the major component, but anything from pentane up through dodecane is often present in the gas. And then we get into fuel components as we get into the heavier hydrocarbons and paraffin wax for the really heavy hydrocarbons. Like icosane has also some asphalt applications. So lots of neat stuff here with the alkanes and differing physical properties and differing uses for the gases compared with the gases that are close to liquids at room temperature and the liquids and then solids at room temperature and pressure. So we hinted earlier that things are going to get a little more complicated when we make rings. And so the cyclic hydrocarbons are those hydrocarbons that have one or more rings in their structure. The simplest cyclic hydrocarbon is cyclopropane. Those 3 carbon atoms, instead of bonding in a straight chain, they can bond back on themselves and make a ring. There's a fair deal of strain in this ring. If you know your angles, right? A triangle would like to have 120 degree bond angles here in this perfect equilateral triangle, and that's not a good bond angle for carbon bonding generally, at least not for saturated hydrocarbon bonding. So there's a lot of strain, but it does exist, and it's relatively stable enough to exist. So that's your simplest cyclic hydrocarbon, although 4 rings, 5 rings, and in particular 6 rings are much more preferred in nature. And if you look carefully, you notice that there's the same issue that we talked about, where you have 3 carbon atoms and only 6 hydrogen atoms. So here with a cyclic hydrocarbon, you're going to have, instead of CnH2n plus 2, if it's just a single cycle in there, it'll be CnH2n for your generic formula from the number of carbon atoms. And so here we see the cyclic hydrocarbons. When we name them, we use the term cyclo so that we understand they're a ring. And so we have cyclopropane, cyclohexane, cyclohexene when we talk about the alkenes. But these are some examples of the ring structures. And you notice we have a little trouble showing all the atoms even in a condensed structural formula type fashion. So what we tend to do in organic chemistry pretty quickly, once we get the hang of things, is we just leave all the atoms off. So cyclopropane, wherever those 2 lines intersect, that point is understood to be a carbon atom, and it's understood to have enough hydrogen atoms to complete its bonding pattern. And so that's where you see cyclohexane and cyclohexene. they differ only by that double bond between two carbon atoms. And that's what we're going to talk about as being the difference between the alkanes and the alkenes and alkynes. Okay, so the alkenes are hydrocarbons that contain at least one carbon-carbon double bond. So because of that, because the carbon has decided to bond again with itself instead of forming additional bonds to hydrogens, their general formula is CnH2n. That's if they have just one double bond between two carbon atoms. Okay, and the way that we would name it, we'd name it very similarly to the alkanes. We'd use the same prefixes to denote the number of carbon atoms, but we'd follow it by the suffix "ene" instead of "ane." That's how we can tell an alkene from an alkane. And we saw cyclohexane versus cyclohexene on the previous slide. Now, since we need carbon-carbon double bonds, we can't have anything simpler than ethylene or ethene because one carbon atom can't make a double bond with another carbon atom. So ethylene, or more correctly, ethene, is the simplest alkene. Now finally, alkynes are hydrocarbons that contain at least one carbon-carbon triple bond. And so because now you've taken away another bond from the carbons that would have gone to hydrogen, their general formula is CnH2n minus 2. So CnH2n plus 2 for a straight chain alkane. Cn2n would be the general formula for a straight chain single alkene. And CnH2n minus 2, now the general formula for a straight chain single alkyne. And just like the alkanes and the alkenes, the name consists of that prefix with the number of carbon atoms. We need to know 1 to 10. But obviously, just like alkenes, alkynes can't form with just a single carbon atom. So you'd start with eth all the way up to dec for our purposes. And obviously, we can go much higher. We saw icosane. We could have icosine or icosine as well. We would just denote the type of hydrocarbon by the suffix ane for saturated, ene for unsaturated with double bond, and ine for unsaturated with triple bond. And ethine, or acetylene by its old name, is the simplest alkyne. We're going to run into this a lot, where there's an old name like ethylene on our previous slide, or acetylene on this slide. We have to be very careful. The preferred name is ethine, but the very common name of acetylene is going to be represented more often than not. So organic chemistry, I'll teach you the rules that we all agree on, and then you'll also see that we break the rules all the time as chemists by using those old common names. The alkenes in particular, and some of the cyclic hydrocarbons as well, often exhibit what's known as cis-trans isomers. So cis-trans isomerism is a form of geometric isomerism where the isomers have the same molecular formula and the same connectivity, so the same atoms are bonded to the same other atoms, but they differ in how they are oriented in 3D space. So as we look down here, we have 2-butene and 2-butene, and they're both named the same way, but they look different. And there is some energy associated with that bond flip. So technically, on the left, we have cis-butene, where the two carbon groups are on the same side and the two hydrogen groups are on the same side of that double bond. And to the right, we have trans-2-butene, where we have the carbon group and hydrogen group opposite each other on the neighboring carbons of the double bond. So you probably have heard about trans fatty acids, and once we started having to declare them in this country on nutritional information, most everybody went back to the non-hydrogenated cis forms, because we do understand, well, at least we've noted, I don't know that we understand, that there's a higher incidence of heart disease with people who take in a lot of the trans fatty acids. Trans fatty acids don't occur in nature. They're the product of unnatural chemists fooling with nature to hydrogenate unsaturated compounds, but nature prefers the cis, which is on our left-hand side, which doesn't look like the best way. It looks a little more constrained than the trans, but that's the way nature builds its unsaturated fatty acids. So That's an example of cis versus trans isomerism, and it does have a big impact on human health, the cis versus the trans isomer. Okay, so beyond the alkanes, alkenes, and alkynes, we also get these very special hydrocarbons known as aromatics. And so this is, for our purposes, benzene and its related structures. So benzene's a very special organic compound that's incredibly stable. So it's a six-membered ring that's sort of a hexagon where each atom has a bond to hydrogen, and we alternate single and double bonds to each other. But that's not really how it's going on. What's really happening is it's really got like 1.5 bonds between each of the atoms in the carbon ring, and it's what we call delocalized electrons. The electrons can flow very freely through the aromatic structures, and so therefore having a benzene ring can be positive or negative, depending on what properties you want. It tends to be very fatty, and so it doesn't dissolve well in water. That can be undesirable if you need a drug delivered that has to have a benzene type ring structure to it, but also it can make for a very nice way to conduct electricity. Some of these conducting polymers that won the Nobel Prize back a dozen or so years ago are based on these benzene type rings, and this idea of aromaticity, having this delocalized flow of electrons possible. So here we see the idea of those structures, that you have the carbons in the ring alternating single and double bonds. So it's either what we show on the left or what we show on the right, but it's not really either of those. What we see in that image to the far right is a little better idea of these individual orbitals coming together to make these orbitals above and below the plane of the molecule that allow the electrons to flow very, very freely through the molecule. And so that's a special electron configuration, a special way that benzene and other aromatics can handle their electron density. And so instead of showing the alternating single and double bonds, what's typically done is drawing a circle in the middle of the ring. And that gives that idea that it's not really single bond, double bond alternation, but 1.5 bonds going throughout the whole ring. And we see these are related structures to benzene. Toluene is benzene with one of the hydrogens replaced with a methyl group. Ethylbenzene, it's an ethyl group instead of a methyl group. Naphthalene is 2 fused benzene rings. It's one of the mothball formulations. Paradichlorobenzene is the other. But that naphthalene has that very unpleasant odor owing to its aromaticity. And then we see some other options where we can have multiple substituents. We can have 2 methyl groups right next to each other. We call that ortho, the right way to do it, like orthodox varieties of religions believe they have the right way. So the ortho has that idea of right next to one another. Meta, your 2 substituents are spaced out by 1 hydrogen in this case in between them. And then finally, para would be as far away from each other as possible on the benzene ring, so the 1,4 positions. So we typically prefer to say 1,2, 1,3, or 1,4, but you'll often still see ortho, meta, and para, the older names, being used today, especially, as I already mentioned, paradichlorobenzene is another variety of mothball if you're not buying the naphthalene type. Okay, so we encounter it a lot in daily life, and a lot of those old traditional organic names have stuck, even though we have official naming schemes now. Alright, so far we've dealt exclusively with hydrocarbons, so carbon and hydrogen. We can also get chlorinated hydrocarbons, so we're taking a chlorine atom and substituting it for one or more of the hydrogen atoms, and so chlorinated hydrocarbons have many useful properties. A lot of the early refrigerants were chlorinated or fluorinated, or both chlorinated and fluorinated hydrocarbons. Dichloromethane has been used a long time as a solvent and a paint remover. Unfortunately, it's one of our known cancer-causing agents, so it is a carcinogen. We've tried to replace it most places. Trichloromethane, chloroform. You've probably seen that used in movies or TV shows to knock someone unconscious, and it does have that property, but it's more typically used now as a solvent when it's used. It used to be used as an anesthetic, and that's where it gets that idea of knocking people out with chloroform. But now it's considered hazardous, just like we said. Dichloromethanes known to cause cancer, trichloromethanes in the state of California known to cause cancer, and the rest of the states it's a cancer suspect agent, so we try not to use it very much at all. And when we do use it as chemists, we have to take proper precautions with the hoods and all of those other ways of keeping ourselves from being unnecessarily exposed. And I hinted at it briefly on the previous slide, but chlorofluorocarbons are carbon compounds where hydrogens have been replaced by both chlorine and fluorine. So these CFCs, they were early refrigerants, they were effective, did a nice job in refrigerators and air conditioners, but unfortunately they also in the upper atmosphere are pretty effective catalysts for breaking down ozone. So once they get way up there and there's lots of energy available, ultraviolet radiation is enough to knock off one of these chlorines or fluorines and start a cascade whereby ozone is depleted rapidly. That was a problem. We had a hole in the ozone layer. We still do, although not as extensive. And when we banned these things, they're pretty long-lived, but having banned them several years ago now, they have all but stopped in their use and their environmental emissions, and the ozone problem is getting better. It's one of those few environmental success stories. So human activity can have negative effects. We know that. We talk about a little green chemistry every chapter. But if humans change their behavior, things can get better. And so this is a real success story. Getting rid of the chlorofluorocarbons, replacing them with something that doesn't have that same ozone depleting aspect has worked. And hopefully we'll be finding replacements for these carbon dioxide generating fuels, which again are mostly organic compounds that we're burning nowadays. And if we move to other greener technologies, then that can be another success story. So those young people out there, you're going to make these changes and you're going to save the rest of us. So what we just talked about, replacing a hydrogen with a chlorine or a fluorine or both, these are taking hydrocarbons and now functionalizing them, adding what are known as functional groups, atoms or groups of atoms that are attached to that hydrocarbon skeleton that aren't carbon and hydrogen. They're new and different elements involved, and they can give special chemical and physical properties to the compounds. Double and triple bonds even, so where we still have just strictly a hydrocarbon, only carbon and hydrogen present in the compound, having the multiple bonding, the double bond or triple bond between two carbon atoms, is also an example of a functional group because you can do new chemistry there. Saturated hydrocarbons, they're nice, they're predictable. From a student standpoint, you can't ask for a better type of compound, but from a chemist viewpoint, they don't do a lot of chemistry and they're not terribly exciting to most of us chemists. Alright, so here's our table 9.4 from the text, and it gives a nice example of the different types of functional groups present. So alkanes have no functional groups, and they have just the generic RH for their formula. Alkenes or alkynes have either the double or single bond, double or triple bond. Double for alkene, triple for alkyne, and we see the general formulas there. Alcohols have a carbon bonded to an OH group. Ethers have an oxygen that bridges two carbon groups, so the oxygen's in the middle of two carbon groups. So you have a COC bond. Aldehydes, you have a carbon double bonded to an oxygen, and then also the carbon terminates with another hydrogen. And on the left-hand side, you can have another hydrogen for the simplest aldehyde, formaldehyde, or you can have a longer carbon chain possible. Ketones have to be in the middle of a chain, right? You have to have the carbon double bonded to the oxygen in the middle of a chain. That's how the ketone differs principally from the aldehyde. They both involve carbon-oxygen double bonding, but aldehydes terminate with a hydrogen, whereas ketones are in the middle of a carbon chain. Carboxylic acids look sort of like a combination between an aldehyde and an alcohol. So instead of just a carbonyl, carbon double bond oxygen, terminated with a hydrogen. Now you have an OH group on the one side, and then an R group or a hydrogen on the other. Esters, instead of the ether COC bond, you have still the COC bond, but it's an ester because one of the carbons has a carbonyl, a carbon double bonded to an oxygen. And then finally, amines, you have a carbon-nitrogen bond, and then the nitrogen's bonded to 2 other groups, the carbon's bonded to 3 other groups, as we see there. They can either be hydrogens or carbon groups. You can have a primary amine, which is the left case that has just the one carbon-amine bond, or you can have a secondary amine with the nitrogen bonding once to a hydrogen and then on either side to a carbon group. And finally, you can have the tertiary amine, the nitrogen bonded to 3 different carbon groups. And finally, amides or amides, as they're known, you have carbonyl, carbon double bond to an oxygen, and then that same carbon's bonded to a nitrogen. So similar to the amine, but the amide or amide has a carbon double bond oxygen. So when we have alkyl groups as the substituents, these are derived from the alkanes. So if we have a group that looks like propane bonded on some other structure, we call it a propyl group. If we bond in the middle carbon instead of one of the end carbons, then we have what's called an isopropyl group. So isopropanol, rubbing alcohol, for those who've been to the drugstore recently to get that for whatever reason, it's a nice way to remove some sticky glues or to clean the skin before putting on a band-aid or something like that. Isopropanol has the OH group on that middle carbon. That's why it's an isopropanol instead of just a straight chain propanol. We have butane groups. They're known as butyl groups or sec-butyl groups. You can have isobutyl groups or tert-butyl groups. Those look like sort of the letter T added to a structure. So these are the typical alkyl groups that you might see as part of a larger structure. There's also an ethyl group. We didn't show that because it doesn't have any other possibility than being C2H5, and then a methyl group would just be a CH3 bonded to something else. Alright, we already mentioned the alcohol group, the OH functional group, and alcohols are very common in nature. The typical ones that we might encounter, methanol is known as wood alcohol. That is not good for us to drink. It can cause blindness and then death if you continue to drink even more of it. Ethanol is the one we tend to drink as humans. That's the one that yeasts will make, and it's in your alcoholic beverages, beers and wines, and if you're of age, you can enjoy those in moderation. Certainly not driving if you've had much, if any, alcohol. And then finally, 1-propanol would be a straight chain. We looked at isopropanol, where instead of the OH group being on that last carbon, it's on the middle carbon. And that would be isopropanol or 2-propanol, and that's the one that's sold as rubbing alcohol. Again, not an alcohol to drink, but an alcohol that has its uses for removing goo and other issues on the skin. I know if you give blood and they put that iodine tincture on you, it's nice when you get home if you just take some rubbing alcohol to get that off. So looking at methanol or methyl alcohol in particular, I think I even mentioned it in the previous slide. It's also known as wood alcohol. It's an important solvent. It's added to automotive fuel and also possibly a fuel replacement in the future if we can move to fuel cell technology. There's a lot of research on the methanol fuel cell. So it's toxic to humans, but again, as long as you're using it safely and not inhaling large amounts of it or drinking it, it's not especially harmful to you and would be a nice option for a fuel cell technology. Unlike the hydrogen fuel cell, where you'd have to have high pressure gases in vehicles, methanol is a liquid. It would be a lot like our current infrastructure. Instead of using the current octane-based hydrocarbon fuel, we would use a methanol-based fuel. You could pump it out and it wouldn't change things too much, but it again holds some promise there. Lots of work to be done by you future chemists to make that a reality. Ethanol is the ethyl alcohol, the type that we consume as humans if we choose to and we're of age and it's permissible. It's also known as grain alcohol. It's added to automobile fuels as well, right? In New York State, you see the 10% ethanol added at most of our gas stations. And that's just to increase the amount of oxygen there, and it actually decreases miles per gallon, unfortunately, but it is helpful to provide some additional oxygen in with the fuel. And it's another one that's considered as a gasoline replacement, especially in the Midwest where they make a lot of ethanol from grain. They would like to see this happen, but it would drive the price of ethanol up quite a bit, and so it hasn't come to fruition yet. E85, 85% ethanol was touted several years back as a good middle of the road temporary fix where you still have some gasoline and some ethanol, and a lot of car engines can handle E85, but I don't know of many places nearby that sell it. Alright, and so, not to narc on anybody's enjoyment of ethanol, but alcohols are toxic. All alcohols are toxic in the right quantity to human beings. Methanol can be toxic in fairly small amounts because it's oxidized to formaldehyde in the liver, and formaldehyde's a poison, can cause blindness or death. We often use it to fix dead tissue, so that tells you it's not too good for living tissue. And even that has been replaced in a lot of morticians' offices. They're using replacements that are less harmful than formaldehyde to human health. But as I said, ethanol is toxic. Unfortunately, college students tend to be the target population for ethanol abuse, and in our area, more so across the river at Binghamton University, there tends to be a couple of cases of alcohol poisoning each year, especially in the fall when first semester freshmen first begin to enjoy that freedom and experiment with things. And unfortunately, it can lead even to death. So you have to be careful, especially with ethanol affecting judgment. The more you drink, the less logical your decision making, and unfortunately with the peer pressure and those sorts of settings, some people will drink to excess, and alcohol poisoning, if caught early enough, can be reversed in the hospital, but if it goes too long, it can lead to death. We also have fetal alcohol syndrome. Ethanol, the alcohol we drink, is the #1 teratogen, birth defect causing substance that pregnant women will sometimes consume, either knowingly or unknowingly, and fetal alcohol syndrome is what happens to the offspring of someone who abuses alcohol while pregnant. So looking at the textbook, we also see a relationship between drinks consumed, blood alcohol level, and behavior, and obviously if you've had just a couple drinks, 2 drinks, and we talk about what the drinks are, again, bottles of beer, or smaller amounts of wine or fortified beverages. A little bit doesn't seem to do too much. A couple of drinks for most of us, if you're above 100 pounds and, of age and all that stuff, it's usually not too much to cause too much impairment. But beyond that, in New York State, 0.08 or higher blood alcohol content is driving while intoxicated. So if you've had 3 or 4 drinks, you're likely beyond the legal limit to get behind that vehicle. So hopefully you've made arrangements in advance that you don't need to be driving anywhere. You've got your designated driver, because things can get very dangerous for everyone, for you and for those around you, if you're driving after having that much alcohol. And as we see, when I mentioned before, college students in particular might get involved with this heavy binge drinking, where consuming 20 or more of these drinks in a short period of time can lead to death. So it's not a joking matter at all. It's something to be very safe about. Alcohol has been enjoyed by humans for thousands of years, and again, most people have no long-term damaging effects, but if you drink in excess, there can be very serious consequences because ethanol is poisonous in those high amounts. Alright, so ethanol and methanol, two of the alcohols we talked about in detail already, they have just a single OH group. You can also have alcohols with multiple OH groups, and they get a special name here. So the glycols, the ethylene and propylene glycol, where you have two OH groups right next to each other, so on neighboring carbon atoms, you get this feature, and they're often used as antifreezes. So they have interesting behaviors as temperatures go down. They don't freeze as quickly as the same sort of structure that has just one alcohol or no alcohol groups. Glycerol is a very common biomolecule. It's triglycerides, and I'm sure you've heard the term if you don't know what they are, and we'll talk about them in particular in later chapters. But glycerol and 3 fatty acids is how we make these triglycerides. Glycerol itself is useful as a lubricant, and it's, again, very well tolerated by humans because glycerol is an important biomolecule. So talking about OH groups, OH functional groups, we have the traditional alcohols that we've talked about, and even the diols, the ethylene glycol or propylene glycol, and then the triol of glycerol. We also have the possibility of replacing a hydrogen in a benzene type structure with an OH group, and we call these phenols. They're really special alcohols. They have that OL ending, but the presence of that aromatic ring alters the properties, as you see here. So they don't act like alcohols, but they act more like acids. They tend to donate that proton, and they also tend to be quite effective antiseptics. So Listerine has a phenol functional group, and it's a very powerful killer of pathogenic and non-pathogenic bacteria as a result. So a lot of antiseptics have one or more phenol groups present. Okay, so ethers, instead of having an OH group at the end like an alcohol, an ether has an oxygen group as a bridge in the middle of two hydrocarbon groups. So we see here the general formula of ROR or ROR prime. Those R's denote some organic group, and they can be the same. That's why we see the ROR, or they can be different. That's what that ROR prime means, where the two carbon groups are different. The most common ether, the one that we typically mean when we say ether, is diethyl ether. So that's an example of having the same carbon group, an ethyl group, on both sides of the oxygen. And diethyl ether is the ether that was used as an anesthetic, and was used before we had other anesthesia options to keep patients sedated during procedures. So it's been around a long time, and it's still used commonly in organic chemistry for other purposes today. Here we see an example of a cyclic ether, that ethylene oxide with the carbon-oxygen-carbon sort of cyclopropane type ring there, with one of the carbons from cyclopropane being replaced by that oxygen. Lots of ring strain, very reactive compound, and it reacts nicely with water to make ethylene glycol. You see that H+ above the reaction arrow indicates the need for an acidic catalyst to make that reaction go forward at any appreciable rate. So that's what we'll typically see is catalyst present above a reaction arrow to let us know that's important for the chemistry. Okay, on to aldehydes and ketones. Again, related, although different structures because of the way that carbonyl, the carbon double bond oxygen functional group, is situated. So in an aldehyde, the carbonyl has to be at the end. It's terminal. There's a hydrogen on one side to end the structure, and then a carbon group on the other side. For a ketone, that carbonyl, the C double bond O, has to be in the middle of some carbon groups. That carbonyl carbon is bonded to carbon groups on either side. And they can be the same. The R groups could be the same, like in the case of acetone, or 2-propanone, as it's officially called. You have a methyl group on either side. Or they can be different. You could have a methyl group and an ethyl group, so on and so forth. So a ketone has to be at least in one carbon in anyway from a structure, whereas an aldehyde has to have the carbonyl at the end. And we see some pictures of that at the far left. We have the simplest aldehyde, formaldehyde, and it has hydrogens on either side. It had to have a hydrogen on one side, but the other side didn't have to be hydrogen. In this case, it is hydrogen. It's a very simple aldehyde. The next example, we have the aldehyde functional group and then a methyl group. That would be a slightly more complicated structure. And then finally, now we see the ketone on the far right. It happens to be the ketone I mentioned, 2-propanone, or as it's more commonly known, acetone. And that has the carbonyl in the center and a symmetrical arrangement of methyl groups on either side. Okay, our last few functional groups now, carboxylic acids. Carboxylic acids are organic acids that contain this carboxyl group. So C double bond O and then C single bond to OH. And then that carbon can be bonded to another carbon group or just a hydrogen, depending on the specifics. So here's an example where that R group is a benzene ring. And so in this case, because the benzene is our substituent, we call this benzoic acid. Most of the hydrocarbons, the carboxylic acid groups will give rise to this name that ends in oic acid. A few have common names, but official names should all end in oic acid for carboxylic acids. Alright, making use of that carbonyl again, now we have the esters, and so esters are formed by taking that hydrogen of the carboxylic acid and then putting an OH instead. So we see here a carboxylic acid and an alcohol reacting to form an ester, and there now we get the C double bond O, the carbonyl, bonded to an O, bonded to another carbon group. So sort of combining that idea of the carbonyl along with an ether, which was a COC bond, and here we have an ester. And esters tend to have strong odors associated with them, many of them pleasant fruit-type odors. So looking at the odors of some common esters, we have methyl butyrate, which has the fragrance of apple, or ethyl butyrate, changing that methyl group to an ethyl group on the one side, gives the difference between apple and pineapple. And then propyl acetate as opposed to pentyl acetate, we have pear versus banana, and so on and so forth, for these really nice fruity flavors or fragrances, depending on if you're smelling or ingesting the esters. Naming esters gets to be fun because it makes you think about the parents that made that ester. So you name the alcohol component first, and then the root name of the carboxylic acid, drop the E and add the suffix -ate. So, for example, methyl butanoate would have come from the methanol reacting with butanoic acid. So that's how we view our esters, and it's easy to know which one was the parent acid because it's the one that has the carbonyl on it. And then the parent alcohol is the O portion of it. So it's the hydrocarbon after the O, or whatever the derivative might be. Okay, now on to amines and amides, and these are nitrogen-based heteroatoms. So heteroatoms, when we say that word in organic chemistry, we mean something other than carbon or hydrogen. And in this case, our functional groups that we've talked about, the heteroatom has largely been oxygen so far. Now for the amines and amides, we have the nitrogen heteroatom. And so when one or more of the hydrogens from ammonia, our NH3 parent structure, gets replaced with an alkyl group, we get an amine now. So like ammonia, amines tend to be basic, and they tend to have very unpleasant odors, very fishy type odors, much like the odor of ammonia, although more dead fish rather than sort of that unpleasant, sharp cat urine type smell. So we see some structures here, amphetamine, having that amine functional group, as does cadaverine, and you have an idea probably what that would smell like, decaying flesh, very unpleasant odor for those amines. 1,6-hexane diamine, probably very unpleasant odor to it. I worked a lot with diethylamine, and that was not a very pleasant odor, to say the least. And pyridoxamine there in the bottom right as another amine, so unpleasant odor, and some other functional groups there that might give that some interesting properties as well. So amides have nitrogen bonded to a carbonyl atom, and that amide group or amide group, depending on the pronunciation you hear, gives rise to the linkages of amino acids going into proteins, or at least polypeptides. So what was formerly known as the peptide bond, and the biologists will still use that term, the chemists recognize it as an amide and use the term for amide linkages instead of peptide. Alright, so most of the heteroatoms that we've talked about, the functional groups, are straight chains. They can also be heterocyclic compounds. So the ring can have atoms other than carbon, and I think one of our rings there for the pyridoxamine also had a nitrogen as one of the ring members, and so that happens a lot. Most organic heterocyclic compounds contain nitrogen, oxygen, or sulfur as ring atoms, and so those are the main ones to look out for. Other ones are possible, but those are the most common examples. So if we think about our amines, where nitrogen is the heteroatom, we can have alkaloids, which are naturally occurring amines. And many of them have physiological effects, and sometimes they're heteroatoms in a cycle. So pyrimidines have that sort of nitrogen alternating double single bond, with nitrogen as two of the members in the 6 ring, so 4 carbon atoms and 2 nitrogen atoms. The nitrogens are spaced by 1 carbon on the one side and spaced by 3 carbons on the other side, and that's a pyrimidine. We also have the purines, which have that pyrimidine type ring, and then fused to it is a 5 ring with 2 of the 5 positions being occupied by nitrogens. And so those are your standard base pairs in DNA, the purine and pyrimidine type functionalities. And so again, there's specific ones: adenine, thymine, cytosine, and guanine, but the classes are either pyrimidines or purines. Okay, so lots and lots of dense material in this chapter, and these ideas are going to come back again and again throughout the remainder of the course, especially as we go into our formal biochemistry chapter. But it's good that you have a basic understanding of this material, and hopefully it comes naturally. Probably a lot of you who struggled with the math so far are feeling a little more comfortable now, and those of you who maybe felt more comfortable with the math that we've been doing maybe are feeling a little uncomfortable now that we've gotten into organic chemistry. But I'm here to help in either event, so whether you're still struggling with the math and need to talk, or whether you're finding this new organic chemistry topic challenging, send me an email, give me a call, let's get together to meet if possible.